Single elementary reaction, we can say that single reaction for each reaction. Okay, right, let's say we have reaction 1, reaction 2, okay, and then when the reaction 1 is combined with reaction 2, we're going to get the overall equation. So elementary step is a single reaction for reaction 1 and reaction 2. Okay, reaction mechanism is a sequence of elementary steps that lead to product formation that we tell what happened on the molecular level and in what order. Okay, and also it tells us which step of the reaction is fast and slow when it's involved mechanism. Okay, let's see here. This is an example of molecularity and also elementary reaction and how we write the rate law. For example, unimolecular. Unimolecular refer to single molecule. For example, A just produce products. Okay, that rate is equal to Ka only. But if you have bimolecule, means that you have two molecules, either A plus A or A plus B, okay, where is produced products. So rate, if A for A plus A, that will be equal to Ka2, okay. But if you have A plus B, your rate will be Kab, right. So termolecular, it means that you have three molecules or more, right. So it could be A plus A plus A, or A plus B, or it could be A plus B plus C, where both all produce products. So if you have triple A, that will be rate is equal to Ka cubic. But if you have A plus B, so Ka squared times by B. If you have ABC, so ABC. Right. So now you must know what is rate determining step. Rate determining step is step which is slower than the others. It's the slowest step. Okay, the overall rate of the reaction, which one would measure if you did some experiment, is controlled by the rate of the slowest step. Intermediate is something that appear in the reaction mechanism or elementary reaction but do not in overall reaction. Okay, the intermediate always form in early elementary step and consume it later. So that's why it's still not produced in the balance or overall equation. Okay. Catalyst normally is species that appear in the elementary step but not in overall equation. So this species present at the start of the reaction and at its completion. Okay. For example, now we give you example. Okay, step 1 and step 2. Step 1 involve this one, which is written as slow here. It's mentioned as slow. And step 2 is fast. So how we write the rate law? Okay. So you have to combine step 1 and step number 2. Combine both, and which intermediate that involve. Intermediate is something that the same you can cancel out. Left and right, it must be cancelled left and right, okay, and right and left, okay. Alright, so in this case, we got the overall equation is NO2 plus CO produce NO plus CO2. Okay, our intermediate is easily to be identified, NO3, and rate is from your overall equation, but you have to be careful. First thing first, you have to check your reactant. Is it the compound or molecule involved in the slow step, rate determining step or not? Okay, so now in order to write your rate is equal to K concentration of NO2 coming from here. NO2 is involved in rate determining step, so you can include N, and also CO. Okay, in this case, in the rate determining step, there is no CO involved. So one CO is not involved in the rate determining step, so it would not appear in the rate law. So that's why your rate law is just here. Take extra careful. When it comes to rate law, you have to compare your overall equation with the slow step or rate determining step. Is it involved in the rate determining step or not? If let's say the substance is not involved in the rate determining step, so no need to include into your rate law. Okay, how about if you have your reversible? Okay, your reversible equation like step number 1, and so you have normal reaction like step number 2. Okay, but just now for any reversible, it becomes so fast. Reaction is so fast because the equilibrium happen here. NO2 produce Br2 and then produce plus Br2 produce NOBr2, and then from NOBr2 it can produce Br2 and NO. So the reaction is very fast. But for step number 2, this is become slow because NOBR2 that's only being consumed here with NO to produce NOBR. Okay, so for any fast reaction, you have to come out with this one. K forward, whatever being forward, we call it as K forward. Whatever being reversed, this one is being reversed to here. Okay, we call it as K reverse. So means that for any equilibrium reaction, for any reversible reaction, you're going to have two K value, rate constant. Alright, so you have to find both. So how? You have to do this stoichiometry first. K forward, what being forward? This one is being forward. NO plus BR2. K forward and OBR2 is equal to K reverse. What is being reversed? And OBR2. Okay, this is one. Okay, once you have that, you have to rearrange K forward over K reverse. Okay, find one topic. Okay, let's say we say NOBR2 will be the topic. Is equal to KF over KR times by NOBR2. This is just you rearrange the equation. Okay, make it this one as equation number 1. Okay, then now you leave it here. So you settle. Once you get KF over KR, okay, that is settled. Alright, so you can move on to step number 2, which is a slow step. Slow step, rate is equal to K1, just put K1, NOBR plus NO. That's it. Okay, so now you're going to solve. Okay, this one you say this is equation number 2. Okay, so now you substitute fast in slow, or you substitute number 1 in number 2. So number 1 we have NOBR can be substituted here. All this value can be substituted here. Okay, so K1 remain. NOBR is equal to KF KR, so you put KF over KR, NOBR2, okay, and then come back here, NO. Okay, this is come back here. This is just replacing everything. Okay, so that will give you K1, KF, KR. They actually just replace it by K. This is just a rate constant, so all of them are constant. We assume all of them are constants. You replace with K. That will give you NO times NO. That will give you NO power of 2 and BR2. This is your rate law for the step 1 and step 2 when you have a reversible. Okay, once again, when you have a reversible reaction, you have to take care when you have K forward and K reverse at the same time. So you must come out with KF stoichiometry with the K reverse. Whatever being forward must be written here, whatever being reverse must be written here. Okay, and then find the KF over KR, rearrange the equation, make it as equation number 1, and then solve for slow step number 2. That will give you normal K1 and OBR and O. Okay, that is reaction number 2. And then substitute fast in slow or number 1 into number 2. Okay, you got this one K, KF, KR. Don't worry about here. This is just a coefficient. Okay, so you can replace with the K, so because the value are similar. Just time out these two, so NO power of 2 BR2. Okay, so now you have the exercise. Can you do this exercise? Okay, you have the reversible. When you have this reverse, you have to find K reverse over K, K forward over K reverse. Write the overall reaction from that. Okay, and then what catalyst in the reaction? Catalyst means it exists in that, but it's not being consumed in the reaction. Which step is a rate determining step? Rate determining step obviously put for the slow, and then derive the rate law. Okay, from here you already can get the rate law. Okay, right, and then catalyst. We know the catalyst is substance that increase the rate of reaction without it itself being consumed. Catalyst, it can happen in two types. We have positive. With the catalyst, positive is going to speed up the reaction. But if inhibitor, for example, inhibitor, that is a negative catalyst. Normally, the function is to slow down the reaction. Okay, only a small amount of catalyst is needed in order to achieve a large or big jump in the reaction rate. Okay, catalyst will lower down the activation energy. When you add the catalyst, it will lower down the activation energy. So what will happen? Your reaction will become much faster. Okay, so we have a few type of catalysts like homogeneous and heterogeneous catalysts. So homogeneous catalysts, normally they are present in the same phase as the reactant. Usually is liquid. For example, we have acid catalyst or base catalyst. But for heterogeneous catalysts, normally they are present in different phase of the reactant. Normally this is applied into solid or the reactant that either gas or liquids. So, for example, Haber synthesis of ammonia, Oswald process in production of acid nitrics, or catalytic converter. So, these are among the solid or gas or liquid catalyst, which is homogeneous, heterogeneous. Right. So, next thing is enzyme. Enzyme normally is a biological catalyst. Okay, it's very highly specific. It's act only on certain molecule that we call as substrate. Enzyme always must be paired with a substrate where we call it as the reactant. Typically, a large protein molecule that contains one or more active site. Okay, this is an example of enzyme where it fit into the active site of the enzyme, substrate fit into it, just like a key fits into a lock. Okay, look at how substrate, and this is the enzyme. Enzyme is very specific. The shape is very specific. Let's say it's want to lock the substrate that has this kind of shape, which should match with it itself, so it can lock, okay, or interlock here. Right, so that is function of enzyme substrate complex, where in the end, enzyme itself can produce the products and also the other different products here. Okay. It can modify its shape to accommodate more than one type of products. Okay, in the end, that's a function of enzyme. Right, for revision, I want you to do this exercise. Okay, in order to emphasize your knowledge and also understanding. Alright, try to do this one. This is a revision from the beginning. Right, and that. Thank you.